In this presentation, we shall analyze the one-dimensional longitudinal movements, that is the movement parallel to the spring orientation of a one-spring, two-mass system. This is the simplest possible system with oscillations. From the force balance equations of this system, we get only one valid allowed configuration of the disturbance. That is, the given disturbance has to be of one particular kind or form. That is, if m1 and m2 are the two masses attached to a spring of spring constant k, then according to the force balance method, the system can have only one particular frequency. That is, omega equals square root of k by m1 plus k by m2. And one particular ratio of the amplitudes. That is, alpha is defined as the ratio of the oscillation of the oscillation amplitude of the second mass, this amp2, ratio of amp2 to amplitude of the first mass, amp1. So alpha equals amplitude 2 by amplitude 1, which turns out to be minus m1 by m2. This is called the normal or the fundamental mode of this spring mass system. No other form of disturbance is allowed on this system. That is, every time this system is disturbed, it should end up having this same frequency omega and this same ratio alpha. No other frequency or no other amplitude ratios are permissible according to the force balance equations. So for this spring mass system, only valid state according to the force balance equation analysis is this omega and this particular alpha. However, from the energy conservation equations, we get an infinite number of solutions. And this normal mode solution found using the force method is just the maximum frequency solution among all possible solutions. That is, this omega is the frequency maxima we get from the energy method. We possibly get a complete set of oscillatory solutions only from the energy method. So how does that solution look like? From the energy method, we get a generalized frequency which is linked with the amplitude ratio. Different amplitude ratios, alpha, are associated with different frequencies of oscillation. That is, the frequency omega is a function of alpha and it is equal to omega equals square root of k into alpha minus 1 square divided by m1 plus alpha square m2. Note here, there is no restriction on the amplitude ratios and all ratios are allowed. That is, alpha can be any real number from minus infinity to plus infinity. In this presentation, we will analyze this spring mass system with both the force balance method and energy conservation method and study the differences between them and check if one of the methods is superior to the other. Let us first look into the force balance method used in standard textbooks. Masses m1 and m2 are connected to the two ends of a spring with spring constant k. This indicates the relaxed state of the spring. Let x1 and x2 indicate the displacements of mass m1 and m2 from their resting position. When x1 and x2 are 0, or when more generally x1 is equal to x2, the spring is relaxed or in its natural length and the masses are in their original resting position. Any deviation from 0, that is, if x2 minus x1 is not 0, then it indicates that the spring is stressed and the masses are not in their resting position. If the masses are set into motion along the x-axis, then according to the standard textbooks, the force balance equation of the longitudinal oscillation of the masses can be written as these two equations. This is for m1 d square x1 by dt square minus k into x2 minus x1 equals 0. So this is for mass 1. And m2 d square x2 by dt square plus k into x2 minus x1 equals 0. So this is for the second mass. Now there are two equations and two unknowns. So we need another equation So what we do is assume the solutions have a sinusoidal form function for x1 and x2 for the displacements. That is, let x1 equals c1 cos omega t and x2 equals c2 cos omega t. They have a common frequency omega. In these sinusoidal functions, c1, c2 and omega are constants and t is the time. c1 and c2 are the amplitudes of oscillation and omega is the frequency of oscillation. Using these x1 and x2 forms in the original force balance equation and simplifying, we get this equation: minus m1 c1 omega square minus k into c2 minus c1 equals 0, minus m2 c2 omega square plus k into c2 minus c1 equals 0. In fact, it should be enough to assume that x1 and x2 maintain a constant ratio, that is x2 equals alpha x1. In these x1 and x2 equations, the amplitude ratio is alpha equals c2 by c1, which is a constant. c2 is the amplitude of mass 2 and c1 is the amplitude of mass 1. And they are constant, so the ratio is also constant. Alpha equals c2 by c1 equals constant. We need not assume the sinusoidal form as such. We get the same solutions using the assumption x2 equals alpha x1, where alpha is a constant, a proportionality constant between x2 and x1. We shall look at that later in the presentation. Adding these two equations that we got from the force balance method using the sinusoidal solution assumption, these two equations, we get this equation, which ultimately implies that c2 equals minus m1 by m2 c1. So this minus m1 by m2 is the ratio of amplitudes. c2 by c1 equals minus m1 by m2. Using this c2 back in one of these top two equations, we get the value of the frequency as omega equals square root of k by m1 plus k by m2. This equation implies that the one spring two mass system can have only one frequency of oscillation, this omega, and only one form of disturbance where the amplitudes are in a particular ratio, this minus m1 by m2 ratio. No other form of disturbances are supported apart from this. Now let us consider a special case where one of the masses is extremely heavy compared to the other. If m2 is much larger than m1, that is, the second mass is much larger than the first mass, or if m2 tends to infinity, then omega simply becomes equal to square root of k by m1, because this second term k by m2 will be insignificant compared to k by m1. Similarly, c2 becomes approximately 0. Therefore, x2 also becomes approximately 0. Now, this system becomes like the usual one spring, one mass system introduced in the textbooks. We can drop the second equation, that is the equation for x2, because x2 is nearly 0 at all the time, and set x2 equals 0 in equation 1 for x1. That is, in the first equation, put x2 equals 0. So, we get only one force equation left over, that is m1 d square x1 by dt square plus kx1 equals 0. And the real solution to this differential equation is this sinusoidal function, x1 equals c1 cos square root of k by m1 t. This is actually a special case of the one spring two mass system where we have ignored the huge mass attached to the other end of the spring. That is, we have ignored m2, the equation associated with m2, and also we have ignored the variable x2 associated with m2. Since m2 hardly moves when m2 is much larger than m1, this approximation works. If we do not ignore m1, then we get this frequency. If we do not ignore m2, then we get this frequency and this ratio of amplitudes as the solution. Now let us look at a simpler method of solution possible using the force balance equations. So this is the special case. If m2 is much As noted earlier, in order to solve these force balance equations, we need not assume the sinusoidal solution forms. It is enough to assume that during the oscillation, x2 remains proportional to x1. Using this x2 in the force balance equation, we get these equations. m1 d square x1 by dt square equals k into alpha minus 1 x1. m2 alpha d square x1 by dt square equals minus k into alpha minus 1 x1. Adding these two equations, we get m1 plus m2 alpha equals 0, which implies alpha equals minus m1 by m2. Using this alpha back in one of the force equations, for example in the equation for the first mass, we get d square x1 by dt square equals minus k by m1 plus k by m2 x1. From this, we get back the same solutions as we got from the previous method using sinusoidal form assumption. We get the same frequency, same amplitude ratio as before, but in lesser number of steps. So this method is much simpler than the method by assuming the sinusoidal form. So we just need to assume x2 is proportional to x1, x2 equals alpha x1, where alpha is a constant. Now let us move on to the energy based method to analyze this one spring two mass system. We can write the net energy E of the one spring two mass system as E equals half m1 dx1 by dt square. This is the kinetic energy of the first mass. Half m2 dx2 by dt square. This is the kinetic energy of the second mass. Half k x2 minus x1 square. So this is the potential energy stored in the spring. Let us use this assumption x2 equals alpha x1 in this energy equation. Then we get E equals half m1 alpha square m2 dx1 by dt square plus half k alpha minus 1 square x1 square. So we have eliminated x2 from this equation, from the energy equation. We know that if we have an energy equation of this form, that is E equals half m dx by dt square plus half kx square, then we get sinusoidal solution with frequency omega equals square root of k by m and instantaneous displacement. This is the solution as x equals c cos omega t, where c is some amplitude depending on the energy of the disturbance. Therefore, from this energy equation, we get the frequency as omega equals square root of k into alpha minus 1 square divided by m1 plus alpha square m2. And for x1 and x2, we get the functions of this form. x1 equals c1 into cos square root of this omega t. For x2 also we get the same, only in place of c1 there will be c2. The omega t part will be the same. Omega will be square root of k into alpha minus 1 square by m1 plus alpha square m2. Note, there is no restriction on the frequency or on the ratio, this alpha, and the ratio of amplitudes as we found in the force balance method. That is, in the force balance method, there is a restriction on this omega and alpha values. In energy method, there is absolutely no restriction. Different amplitude ratios are associated with different frequency of oscillation, and all real values of the amplitude ratio is allowed in the energy based method. Let us now differentiate this omega square function with respect to alpha. We get d omega square by d alpha as this equation. Let us equate that to 0 in order to find the maxima minima of this omega square. Then we get k into alpha minus 1 square by m1 plus alpha square m2 whole square 2 alpha m2 is equal to 2k alpha minus 1 divided by m1 plus alpha square m2. So in this equation, if alpha equals 1, then also this equation is satisfied. But when alpha equals 1, we get omega equals 0, because omega is a function of alpha like this. It depends on alpha minus 1. So this is a trivial solution, whatever is described at alpha equals 1, which implies the spring mass system do not have any oscillatory solution under this condition, and both the masses translate with the given velocity without oscillating. That is, when both masses are disturbed with the same initial velocity simultaneously, then the whole system translates without oscillation. This is what happens when alpha equals 1. when alpha is not equal to 1, we get the ratio alpha equals minus m1 by m2. That is, if we want d omega square by d alpha equals 0, so these are the two equations, either alpha equals 1 or alpha equals minus m1 by m2. So that is, we get the same alpha as in the force balance method. So we got the same minus m1 by m2 from the force balance method also, and the same omega that we got in the force balance method. This means this omega is either a maxima or a minima at alpha equals minus m1 by m2. Turns out this omega is the maxima. This is the maximum possible value of frequency for this system. We can say the force method only captures the maxima minima frequency states amongst all the possible states given by the energy method. The states captured by the force method are called the normal or fundamental modes. So what about the disturbance with other values of alpha? That is, under the non-normal mode condition, when alpha is not equal to minus m1 by m2 and omega is not equal to square root of k by m1 plus k by m2. Rearranging the omega square equation, we get this quadratic equation in alpha. For a given value of alpha, there is only one value of omega square. But for a given value of omega square, there can be maximum two different values of alpha. Solving the quadratic equation here, we get these two values for alpha. So these are the two values of alpha we can have at the same omega square value. At omega equals square root of k by m1 plus k by m2, the discriminant becomes 0. That is, this factor inside the square root symbol, this becomes 0. So we get only one solution, alpha equals minus m1 by m2 on simplifying this. When the discriminant is non-zero, then alpha can switch between the two values, the positive and the negative solution, without any change in the frequency. So that is, they will have the same frequency value or omega square value, but it will have two values of alpha corresponding to the same omega square. And they will have the same net energy. So the net energy or the frequency is not changing. Still alpha can have two values, two degenerate states or two possibilities. Probably we can assume that alpha switches values every half cycle or pi by omega seconds. These two alpha states in fact correspond to the two states of elastic collision, the before and after collision states between these two masses m1 and m2 for the given net energy and net linear momentum values. That is, when two masses m1 and m2 collide with a certain energy and certain linear momentum, then they will have two possibilities. M1 will have one set of M1 M2 will have one set of before values and after collision values. So these alpha, basically the two possible values of alpha correspond to that. Here P is the momentum measured when the two masses are in their resting position, that is when x1 equals x2, while executing the oscillation. That is, the spring is oscillating, only the masses come to their resting position and the spring is in relaxed state. So at that position we measure the momentum. This is also the position where we see the largest velocity of the masses. And these are the momentum and energy equation at resting position. m1 c1 omega plus m2 c2 omega equals p is the linear momentum, and m1 c1 square omega square plus m2 c2 omega c2 square omega square equals 2e, where e is the net energy of the system. Using c2 equals alpha c1 in the energy equation, we get the velocity as c1 omega equals plus or minus square root of 2e by m1 plus m2 alpha square. Without any loss of generality, we can just pick only the positive or the negative solution for this velocity. Let us pick the positive solution. Using this c1 omega and c2 equals alpha c1 in the momentum equation, we get m1 plus m2 alpha into square root of 2e by m1 plus alpha square m2 equals p. We can consider the initial momentum direction as the positive direction. It is easy to prove that momentum is conserved. If you want to know the full derivation steps, contact us for the detailed PDF file. Using the quadratic solution of alpha that we discussed earlier, In the momentum so using that those two values of alpha in the momentum equation, the quadratic solution alpha that we got earlier, we use that alpha in the momentum equation. We get P equals square root of 2e into m1 plus m2 minus m1 m2 omega square by k. This implies only one value of linear momentum P for a given value of frequency omega square and net energy E. Like in the elastic collision case, we get energy and momentum conservation. So this is same as the elastic collision case where energy and momentum are conserved. The two sets of before and after velocities we get are this velocity 1 and velocity 2 values. The velocity 1 is the velocity of the first mass and velocity 2 is the velocity of the second mass. The positive and negative solutions of velocity 1 are the before and after velocities of mass 1 during an elastic collision. And the positive and negative solutions of velocity 2 are the before and after velocities of mass 2 during the elastic collision. In an elastic collision, net energy and net momentum of the system is not restricted in any way. Energy and momentum can be any values, but in the normal mode solution, only zero linear momentum value is allowed. Let us now consider a few concrete examples, starting with the normal mode oscillation that we get from the force balance method. So this is case 1. This is the normal mode method. Suppose alpha equals minus m1 by m2. So this is what we get from the force balance method. Then omega equals square root of k by m1 plus k by m2. So the momentum we get is P equals m1 plus alpha m2 c1 omega equals 0. This m1 plus alpha m2 becomes 0 because alpha equals minus m1 by m2. Using P equals 0 in the above velocity formulae, we get these velocities for the normal mode solution. So with the V equals square root of 2e by m1 plus m2 into m2 by m1, the oscillation keeps switching between these two velocity states, plus v minus m1 by m2 v. This is the before collision state, and minus v plus m1 by m2 v. One of them can be considered as the before collision state and the other is the velocity value of the two masses after collision. Overall, the two masses keep switching between this state and this state forever. Once disturbed in the beginning, they keep oscillating between these two states, keep switching between these two states forever. So these are the velocities we observe when the masses are in their resting position during oscillation. Here, plus v is the velocity of first mass before collision, and minus m1 by m2 v is the velocity of second mass before collision. Similarly, this is the set of values of m1 and m2 after collision. The before becomes after and after, it keeps switching between before, after, so it keeps switching between those two states. And with c equals this, the amplitude keeps switching between plus c minus m1 by m2 c and minus c plus m1 by m2 c. Basically, this is how the normal mode's oscillation looks. In the first step, the two masses will be at rest in their resting position and the spring will have a relaxed length. We disturb it with velocity v1 and v2 such that the net momentum is 0. Basically, these velocities correspond to the plus v minus m1 by m2 v state described in the previous page. So with this disturbance, the spring gets compressed and at some point both masses come to rest. Note, this is not the resting position of the masses when the spring is relaxed. Here the spring is compressed to the maximum extent possible with the given disturbance. From here they start expanding. So this is the most compressed state. From here they start expanding. The spring starts expanding. During expansion, when the masses come back to their resting position with the relaxed length of the spring, we can see the velocities have reversed their direction. This corresponds to the minus v m1 by m2 v state described in the previous page. The masses continue to expand. When the spring gets expanded to the maximum extent possible with this disturbance, the masses come to rest and start compressing. Eventually they'll compress and reach the relaxed length, and masses reach their original resting position. At this moment, we see the same velocities that we imparted as disturbance in the initial step. And this is reversal of velocities compared to the third step. So this fifth step is same as the first step and opposite of the third step. And all these steps repeat again and again. So this is how the normal mode oscillation looks. The center of mass of this system is stationary since the net linear momentum of this system is 0. Now let us look at one of the non-normal mode solutions where the net linear momentum is not 0. In this case, for simplicity, let us consider the two masses have the same value, that is m1 equals m2 equals m. We give the first mass a disturbance of velocity v and the second mass remains undisturbed. Since C2 is 0 in the first step, the ratio of amplitudes alpha equals 0. From these m1, m2 and alpha equals 0 values, we get omega, that is frequency, as omega square equals k by m, or omega equals square root of k by m. The net linear momentum as p equals square root of 2e by m, which is not 0. Here E is the net energy. So P is proportional to square root of E. With this omega value, we get two possible values for alpha. Alpha can be 0 as seen here, and alpha can also switch to infinity. So alpha can be 0 or infinity. Basically this implies C1 becomes 0 and C2 omega becomes V. That is, when alpha is infinity, this C1 becomes 0. The first mass comes to rest, only C2, the second mass, is moving. So alpha equals C2 by C1 becomes infinity. In the non-normal mode solution, alpha has two possibilities and it keeps switching between the two values. Basically, in one state, the first mass velocity is C1 omega is plus V, second mass velocity is C2 omega is 0. In this state, amplitude of the first mass is C1 equals square root of 2e by k, and amplitude of the second mass is C2 equals 0. Then in another state, velocity and amplitude values are exchanged. That is, C1 omega becomes 0 and C2 omega becomes plus V. C1 becomes 0 and C2 becomes square root of 2e by k. So with V equals square root of 2e by m, the oscillation keeps switching from plus V0 state and 0 plus V state. This case truly illustrates the leapfrogging motion or the earthworm type peristaltic motion of the spring mass system under this non-normal mode disturbance. So this is how this non-normal mode oscillation looks. In the first step, the first or the left mass is disturbed with some non-zero velocity, and the second mass or the right side mass is undisturbed and it remains at rest. Then the spring starts compressing from the left and the first mass comes to rest. At this point, the second mass is triggered into motion. The right side starts expanding. So the left side comes to rest and the right side is triggered into motion. When the spring length becomes equal to its relaxed length, the right end or the second mass of the spring is expanding with given initial disturbance velocity. Since m1 equals m2, the two masses are the same. This velocity in the third step of mass 2 is same as this velocity of mass 1 in the first step. Then the expansion stops. The right side expansion stops. The whole energy and momentum is trapped within the spring. At this point, the first mass is triggered into motion. The second mass comes to rest. The first mass is triggered into motion now. The left end of the spring starts compressing. When the spring length reaches the relaxed length, the first mass has the same velocity as in the first step. We can also notice the whole spring mass system has translated to the right. The center of mass is not stationary anymore. In this case, since net linear momentum is non-zero, the system gets translated according to the momentum value. But it is not continuous. Over a long time, if we see, it would have covered the distance corresponding to this momentum value or velocity. So this fifth step is exactly same as the first step, and the same steps as shown below this repeats again and again, repeat below this, with the whole spring mass system drifting rightward. We can also note that in the first step, alpha equals 0, since second mass amplitude is 0, C2 equals 0, as it is not moving. In the third step, the first mass amplitude is 0, hence alpha equals infinity. The alpha value switches between these two values, 0 and infinity, every half cycle, that is pi by omega seconds, where omega is the frequency of the oscillation. So we will end this video here. If you want a more detailed discussion with more example, ask for the PDF article associated with this video. So in conclusion, the one spring, two mass is the simplest of all the oscillatory systems. The idea of harmonic oscillation and the calculations associated with it are of fundamental importance in various branches of physics. It would be unthinkable to assume there would be shortcomings with such an important concept. In this article, we have shown that the usual force balance method only provides a subset of all possible solutions. This is yet another example which shows that the energy-based method is superior and offers a complete set of solutions. None of these solutions, apart from the normal modes given by the force method, have ever been explored. So the approach proposed here will open up a huge chunk of unexplored physics, offering new insights into old phenomena and better tools to understand newer, less understood phenomena. That's about it. Thank you. Please like and share the video and support the truly indigenous, truly rational physics, neophysics. Thank you.